What happened? Looks like we went from H2O to OH. We went from NH3 to NH4. Somebody lost a hydrogen. Somebody gained a hydrogen. Who lost it? Water lost that hydrogen. So since by definition, if it loses that hydrogen, it's an acid. Okay? Now we don't know that. You can't just look in the equation and assume the strength. Okay? You can look it up and see what acids are strong or weak. We can just see what happens. Okay? This could be strong or weak. Of course, we know that water is not a strong acid. We know that it's a weak acid, but nonetheless. All right, so we lost our hydrogen there. Where did it go? It had to have gone to this base, right? So when you add a hydrogen to this, it's no longer charge neutral. You've brought in a proton, right? You brought in a hydrogen charge. So you're at NH4 positive, okay? Now, let's look. This is your acid. What did it become? It became this, right? So that's going to be the conjugate base. It's going to be the version of this without its hydrogen that it could pull back if it wanted to, okay? That's why OH would be the conjugate base. Now, what happened here? This gained the hydrogen, so it at NH4. Now this did not have one. It was a base that accepted the hydrogen. Now you've got ammonium that has an extra hydrogen, so it can act as an acid if it wanted to. It's probably going to be, this is a very strong base, so that's going to be a pretty weak acid. Okay? This is a very weak acid, so guess what that is? Hydroxides are very strong bases. Those are the strongest bases we can probably get. No, not really. This is just written. Right. It doesn't really matter. It just helps you keep track of the hydrogen is the only reason it's written this way. Okay. Technically, of course, we would write OH negative because that's how we'd write it in a formula form. But this is just to illustrate where the hydrogen went. Okay. So again, here's our reaction. Ammonia water. We just looked at this one. So here's our H2O and our notice what happened. It became OH negative. You see this hydrogen that was lost, so we can visualize it. This is a conjugate acid-base pair. This was our acid here. This was our conjugate base as a result of that. So you should be able to label these in your chemical equations. Likewise, what happened? Likewise, what happened was NH3 gained a hydrogen, as you can see here. So therefore, this base became a conjugate acid. So you should be able to label that as such. So you should be able to write acid, base, conjugate acid. Okay, let's try it. Don't cheat. See if you can do it. Identify the acids and bases and their conjugates. What's this? Obviously, it's sulfuric acid, right? So that means by default, this would have to be the base if you know that this is a reaction, an acid-base reaction. But let's look chemically and find out. We went from this to this. How did we do it? We lost a hydrogen, so we labeled that as acid. We went from this to this. How did we do it? Gained it. So this guy's your base. So if this is my acid, H2SO4 is my acid. If water is my base, what's hydrogen sulfate? My conjugate base. And what's my hydronium ion? Good. Conjugate acid. Let's look at carbonate. Okay? Hydrogen carbonate or bicarbonate. Bicarbonate, we said, that's going to be something very important in human systems. Okay? We have a buffer system that helps control acid-base levels in our body that involves sodium bicarbonate, NaHCO3. Let's see how this works. If you have hydrogen carbonate in water, this is what forms. I almost told you the answer, but H2CO3 plus hydroxide ions. So let's take a look. How did we go from here to here? You gained a hydrogen. If this gains a hydrogen, what is this? This is a base. That's right. That's just how come carbonates and hydrogen carbonates can also be bases, not just hydroxides. Okay? So this was our base. What water must have been? We went from here to here. This was an acid. It lost it. Since this gained it, what is this now? Okay, you're right. I thought you were going to say conjugate base. This is a conjugate acid. That's right. This was the base, right? This gained the hydrogen, so the base turns into now something with an extra hydrogen, thus an acid. So a conjugate acid. What's this? Conjugate base. Now, this is a let's say a reasonably, this is a very weak acid, so this is going to be a strong base, right? This is actually a fairly weak acid, so this was probably a relatively strong base over here. So. No, they don't have to be. It doesn't matter. Yeah, it doesn't matter. Okay, good. Now, we discussed the neutralization reaction back when we talked about types of chemical reactions. Now, we look at this and we see that a neutralization reaction will be when you neutralize an acid and a base. When you take something that is a very good proton donor and something that is a very good proton acceptor, and basically their forces of the way they act cancel each other out. So that, by themselves they could be dangerous. Whenever they're allowed to react with each other, they cancel each other's effects out and leave us with something that's not dangerous. Okay, this is a neutralization reaction. So, like here's hydrochloric acid in this picture, and sodium bicarbonate, baking soda, sodium hydrogen carbonate. What do you get from the result of that? Well, if you pour those things together, or even if you take vinegar and pour it on baking soda, you know that it just fizzes and fizzes, right? Why is it fizzing? Because of what comes out in this reaction. What actually comes out is sodium chloride in an aqueous solution, so it's salt water. What else comes out is the H combines with the other HCO3 to actually give you H2CO3, which is carbonic acid. Okay? But if you remember when I talked about these, when we talked about neutralization and gas evolution reactions, anytime you see a carbonate locked up like this, what you're going to see a lot of times is a gas evolution. You're going to see the CO2 escape from that carbonate. Like in this case, you would have H2CO3. H2CO3 doesn't stick around very long. Okay? As a result, what will happen is H2CO3 will separate out into water and carbon dioxide. So when you pour all this in here, the reason that you're seeing what you see is because salt water is forming, gas is escaping, and also regular just liquid water is forming. Okay? So technically, after all that escapes, you could take something that could, burn you, neutralize it, turn it into this, and drink it, and it'll just taste salty. That's assuming that you've balanced everything out. Now, if you haven't, remember, stoichiometry plays into this. There's got to be one of these react with every one of these. So if you don't have enough of this, and you just pour it and it fizzes, but there's still some HCl left, not a good idea to drink it, right? So you have to think, there's obviously going to be some math involved with this, as we'll get to, but you've got to be able to, if you're going to neutralize this, know how much stuff to mix together based upon stoichiometry so that you get all of this product and none of these left over. Okay? All right. What will always happen, I mentioned this before, but keep this in mind. Acid plus base will always give you salt and water. Now, there may be intermediate things, but that will always be true. Acid, base, okay? Salt and water. It'll be a solution usually of some kind of saltwater solution. It may not be sodium chloride, but it could be some other ionic compound that's dissolved, which is a salt. Okay? All right. There's generally going to be a double displacement reaction, like we showed up here. Like in this case, the sodium and the hydrogen would flip places. The sodium and the hydrogen would flip places, and they each have new partners now. That's a double displacement reaction. So that goes back to some of the stuff we've talked about. Okay. All the other chemical stuff that we've talked about in terms of equations remain the same. We still have to keep track of charges. We still have to write things correctly and all that. So that doesn't change. So take this. We've got sulfuric acid reacting with calcium hydroxide, which is like lime. That's what lime is. We'll give you calcium sulfate, which is gypsum in like drywall material, that kind of stuff, and water. So you could actually take lime, digest it a little bit with some sulfuric acid. You could get sort of a plastery, drywall type wet. Imagine all that like a wet kind of material. That's what would come from this particular reaction. Okay. But this is a strong base, though. And the reason you would put lime like on soil is to reduce the pH. If you have acidic soil, which happens a lot around here, and you spread lime on there, what you're actually doing is performing a reaction. You've got some hydrogen ions that are in your soil, some normal higher pH or lower pH, higher acid levels of soil. You would want to try to neutralize that and bring that pH closer to 7. Make it a little so there's less free hydrogen floating around to damage whether it's vegetation, water tables, whatever. Put some lime on that, they'll interact, and you'll actually perform a neutralization reaction. And you can this is just a salt and water. So those free hydrogens are what's kicker. for biological systems. That can be dangerous, okay, if levels get high enough, or at least it'll reduce yield and that kind of stuff. So, okay, some are gas evolving, like what I said. Whenever carbonic acid forms, you can see that CO2 is trapped in there, so that will actually evolve out. Just keep that in mind. So if we did the same thing with sulfuric acid, but instead of calcium hydroxide, we use sodium bicarbonate, look what we get. We would get sodium sulfate, and then H2CO3, which then falls apart, okay, into water and carbon dioxide.